So, okay, thank you. So today I want to talk about quantum Turing machines and some extension of this model. But to start with, I want to start with a citation. And it turns out that this it comes from a slide, one of the very first slides that we've seen yesterday. But it's adapted from one of the slides of the talk given by Turing. He's not here, unfortunately. So we have this slide, and in fact I have two comments about that. First of all is that here we have some implications. So if we are mad, then we lack this kind of pictures. But if we want to do a piece of logic, here it's just an implication. Okay, it's A implies B. But you can like this kind of logics, this kind of picture, and even if you are not mad. So it's just to avoid any problem with my colleagues and supervisor and so on. Okay, the other remark is that if you are old, you used to work with quantum circuits. But if you are even older, you have worked with quantum Turing machines. Because the quantum Turing machine is the very first model of quantum computation, which has been introduced by Deutsch in 1985. So, and it turns out that this kind of model, this model has to be updated in order to deal with this kind of new interesting stuff. So today, I want to update this model and to introduce the new version 2.0 of the quantum Turing machine. Okay, so more seriously, I will start with an introduction to the quantum Turing machine and then present this new version, the observable quantum Turing machine, and we will be interested in the expressivity and the computational power of this new model. Okay, so let me start with the very beginning, deterministic Turing machine. So I think that everybody knows what is a deterministic Turing machine. So this is the machine. You have the tape with a word, which later comes from a finite alphabet sigma. You have the head of the computation, read and write, which is able to read and write and move. And you have the internal state here. So the description of the machine, the state of the machine, is given by the classical configuration, so the description of the internal state, the finite word which is on the tape, and the position of the head. And the evolution of the machine is described by the transition function. Okay, so for instance, here we have an example. And the important point is that among all the internal states, this internal states here, some of them are halting states. So here, which is represented in red here. So it means that when the machine reaches this state, which is this state, then the computation is terminated. Okay? Computation stops. So here, this is the end of the computation. Okay, so how can we go from classical Turing machines to quantum Turing machine? The idea is that we associate with any possible transition an amplitude, a complex number. Okay? Then the configuration, the quantum configuration of the machine becomes some superposition of classical configurations that I have tried to represent here. So we have some superposition of words, so here 0 and 1. The position of the head is just a superposition of positions, and here we have some superposition of internal states. So it's a mess, but it's like that. So we have this quantum Turing machine. And the evolution of the machine, the evolution of the configuration, can be described by the evolution operator. So if the configuration of the machine is this one, then it becomes this one. This is a linear operator, which is entirely described by the transition function. And it turns out that quantum Turing machine has to satisfy some well-formedness condition. Okay? And according to Deutsch, these well-formedness conditions are used, in fact, for two reasons. First of all, we want that the evolution of the machine does not violate the postulates of quantum mechanics. So it's just a natural condition. But we have another condition, which is that during the computation, the machine is isolated from the rest of the world. Okay? So we have this system, the quantum Turing machine, and this is isolated from the environment. So this is the two conditions which have been given by Dutch. And it turns out that it's easy to formulate this well-formedness condition in mathematical terms. It means that the evolution operator is an isometry and satisfies this property. Um dagger, is the identity. So we have a well-formedness lemma which says that when we give the description of the quantum Turing machine, it turns out that we give the description of the transition function, not the evolution operator. But it turns out that if this transition function delta satisfies these properties, then the evolution is an isometry. And it turns out that this is a characterization. So I don't want to go to the details here, but just to show that it's possible to give these four conditions such that delta, such that the evolution is an isometry if and only if the delta satisfies these conditions. Another important result for programming with quantum Turing machines is the following result, the completion lemma, which says that if you define a partial transition function, so if you give the definition just for some entries, and if this partial transition function satisfies all these conditions, then this transition function can be extended in order to obtain a quantum Turing machine, a well-formed quantum Turing machine. So this is a very useful lemma. Okay, so now what happens at the end of the computation? So we have seen that during the computation, the machine is isolated. And at the end of the computation, the idea is that we want to have a classical outcome. So we observe the machine. We just open the door, and the configuration, which is a superposition, collapses to a classical configuration, which is the outcome of the computation. But it turns out that just before the end of the computation, since the system is isolated, you have no way to know if the halting state is reached or not. So it turns out that there is no way to know if the computation is actually terminated or not. So you wait for a long time, then you measure, and if you are not lucky, then you obtain a configuration which is not a halting configuration, a final configuration. So in order to solve this problem, we can add an halting qubit. So what is the idea? So we have this qubit here, which is not inside the isolated part, but just in the environment. And it turns out that we can measure this qubit, this halting qubit, whenever we want. And when this qubit flips from 0 to 1, it means that the computation is terminated, and we can look at the configuration, observe the machine, and we will obtain the final configuration. So here we have a solution, but it turns out that this is very tricky. And since we have measurements during the computation, this is no more a quantum Turing machine, because the isolation assumption is here not respected.
How can you make that bit evolve if it's outside?
It's tricky. So in fact, for the description of the transition function, you consider that this bit is in fact inside the internal states, but you can measure it, so it's just not well formalized. So, as a consequence, we can see that, in fact, this isolation assumption given by Dutch is probably too strong. So, first we have seen that we have some technical issues, some technical problems with the halting of the quantum Turing machine, which makes the machine not very user-friendly, because you don't know when the computation is terminated. Moreover, since in fact we have learned with the development of quantum programming language that in quantum computation we use the paradigm of quantum data classical control. And it turns out that here there is no way to represent the classical control, since everything is quantum. So it's a limitation of this model. And moreover, it turns out that if we look at the other models of Turing machines, the probabilistic Turing machine or the deterministic Turing machine, in general, they don't have to be isolated or reversible. Okay? This condition is not a usual condition, except maybe for the reversible Turing machine, but this is a very special model of Turing machine. So as a consequence, if you just take your favorite probabilistic Turing machine or deterministic Turing machine, this machine will not be well-formed. So with the quantum Turing machine, we expect to have a very general model, but it turns out that it's just a spatial model of reversible quantum computation. So the idea is that what happens if we consider that the machine is not isolated during the computation, if there are some interactions between the environment and the quantum Turing machine. So we have to model these interactions between the environment and the machine, and we choose to model it using an observation. Okay? We consider that the environment observes, measures the configuration of the machine according to a partial measurement described by the observable O. And this measurement is applied times to times. We consider that it's applied before and after every transition. Okay, so the machine is submitted to the observation of the environment. So we have just one assumption for this observation of the environment. We assume that since the environment is classical, we assume that if the machine is already in a classical state, in a classical configuration, then this observation will not disturb the state of the machine. Okay? So the classical configuration have to be eigenvectors of the observable. Okay? And thanks to this assumption, we obtain that this observable is in fact characterized by a partition of the classical configuration. The idea is that two classical configurations are in the same region if they are associated to the same eigenvector. Okay. So this partition is strongly related to the eigenspaces of the observable. So we have this partition, and we can define the projector for every lambda. We can define this projector, the projector in the corresponding eigenspace. So this is the action of the environment, which is modeled like that. So now we obtain the observable quantum Turing machine, which is a quantum Turing machine, as we have seen before, with the formalization of the environment, which is represented by this partition K of the classical configurations. So MK is an observed quantum Turing machine. And what is the evolution of this machine? So it's described by this linear operator acting on density matrices. And the action of this linear operator is we measure just before the transition, so we measure according to the observable, so we apply one of the projectors, then we have the transition, so we apply the evolution operator of the original machine M, and then we have another measurement. So this is the evolution of the machine, and we have also a kind of well-formedness condition, which is here called well observation, which is that the machine is well observed if this linear operator is a superoperator. This is this condition. Okay, so an example of observed quantum Turing machine. If we consider a quantum Turing machine, then we can consider the bipartition of the classical configurations. On this region, KH, we have all the final configuration of the form KH and something. KH is a halting state. QH is a halting state. And KH bar is just all the other possible classical configurations. And the observable quantum Turing machine defined like that evolves as follows. So we have some superposition of configurations. Then we measure according to this observable. So we have just two possible answers. Either the state is here on the halting state or elsewhere. So, for instance, during the first measurement, we obtain that the halting state is not reached. Then we apply the transition of the function of the machine M. Then we measure it again, and here we obtain that the halting state is reached. Okay, so this is something which is very similar to the halting qubit, but here we have a formalization of that using these observable quantum Turing machines. Okay, so it turns out that this well observation condition is weaker than the original well-formedness condition. What does it mean? It means that if you take a quantum Turing machine which is well-formed, then for any partition of the classical configuration, the machine, the observable quantum Turing machine that you obtain is well observed. Okay, so this model of observable quantum Turing machine extends this original model of quantum Turing machine. So here you have the proof. And it's an even more expressive model because the classical probabilistic Turing machines or deterministic Turing machines, which are not well formed if they are not reversible, are in any case well observed if we consider this full observation of the configurations. So here it means that with this model, the observable quantum Turing machine, we have kind of unification. We are able to express any quantum Turing machine, but any probabilistic and deterministic Turing machine as well. So it's a more expressive model. And it turns out that this model is too expressive, or in fact it is too powerful, because we are able to solve some undecisional problems with this machine, with these observable quantum Turing machines. Indeed, there exists a well-observed quantum Turing machines, as we have seen before, for deciding the problem, the halting problem. That is, for a given deterministic Turing machine and a given input, we want to know if the machine M of U will halt or not. And it turns out that there exists an observable quantum Turing machine to solve this problem, with a high probability and, in fact, almost a constant time. So how does it work? So first we start with the quantum Turing machine, a very simple quantum Turing machine, which is just Hadamard. So here we have the definition, but just look at the action of this machine. So if the initial configuration is Q0 and some word on the tape, then after one transition, what we obtain is a superposition of Q1 and Q2 with the same word W on the tape. Okay? Why? Because here we have a transition Q0, Q1 with amplitude 1 over square root of 2, and here a transition Q0, Q2 with the same amplitude. So we obtain this superposition after one transition. And then the other transition consists in applying the same kind of things. That is, from Q1 we are going to QH bar with this amplitude 1 over square root of 2, and so on. So we obtain this state. And here we can see that we have some interference between this part and this part. So we obtain QHW. So here, this is a Hadamard quantum Turing machine because this is very similar to the application of Hadamard twice. Okay? You apply Hadamard, you obtain a superposition. You apply Hadamard again, you obtain something more complex, but there are some interference such that you obtain a basis state. Okay, so this is the starting point, the quantum Turing machine. And now we have to describe the measurement that we will apply to this machine. And this measurement is related to the problem that we want to solve, that is the halting problem. So here there is a technical part that I don't want to go to the details. You consider an encoding of the machines and the inputs. Okay, so this is something very usual if you use the encoding of a universal Turing machine, for instance. So you have this encoding of the machine and the input, and you consider the following partition. So in K0 you have the configurations of the form Q1, and here the representation of a machine such that MU does not halt. And you add also this kind of configurations, that is when QH bar is reached for any word. And the other configuration, the other region is just all the other possible configurations. Okay, so we have a bi-partition of the states. And so what is the evolution of the machine if we apply this observation before and after every transition? So I just remind you what is the evolution if there is no measurement. So we start from this one, we obtain this superposition, and then this state. Now, there are two possible evolutions for the observed quantum Turing machine. If the machine actually halts on this input, then it turns out that these two configurations, which are the two configurations of the superpositions, are in the same region, in the same set, K1. Okay? Why? Because Q2, all the configurations with Q2 are in K1. Okay? And here, since the machine is halting, this configuration is in K1 as well. So in this case, we apply a measurement, but it turns out that these two configurations are in the same region, so this measurement does not affect the superposition. Okay, so we keep the superposition, and we apply another measurement, but in fact, we have exactly the same evolution as the original quantum Turing machine, because all the states are in the same region. Now, in the other case, if the machine does not halt, then it turns out that the two configurations of the superpositions are in different parts, in different regions. This one is in K0 because the machine does not halt, and the other one is still in K1. So when you apply the measurement, you destroy the superposition, and at the end of the day, you obtain a probabilistic distribution of outcomes. You obtain QH with probability 1/2 and QH bar with probability 1/2. Here the idea is that, so we are saying that the machine is just the application of H twice. And it turns out that if the machine actually halts, then you apply H twice, so you obtain the basis state at the end of the day. But if the machine does not halt, then you apply H, you measure the system, you apply H again, and you measure the system, and you obtain just a random bit at the end. And using this, you can decide with high probability, by repeating this process, if the machine is halting or not. Okay, so here we have a problem, since we are able to solve this halting problem. So this initial definition is not a good definition, so we can try to restrict, to decrease the power of the environment. The point is that here the environment is too powerful, so in order to decrease the power of the environment, we will allow only measurements of the internal state and the position of the head, instead of all the configuration. But it turns out that if we do that, we still have the same kind of property. It's not exactly the same, but we can prove the same. There exists a machine to solve this halting problem. So we have to be more restrictive and just allow finite partitions, in fact. And we consider that K is just a partition of the internal state and and sigma, which represents, in fact, the symbol which is pointed out by the head. So now we have this. So we have more and more restriction. We have now this partition, this kind of partitions, and we can prove that with this kind of partitions, then any observable quantum Turing machine can be simulated efficiently with a quantum Turing machine. So it proved that this model is not too powerful, contrary to the previous models that I have presented. Okay, so I think that I don't have enough time to go to the proof. Okay, so if we consider this definition of observable quantum Turing machines, then we can extend the well-formedness lemma into a well-observation lemma, which is very similar to the previous one. We just have some difference here in red, and it's easy to see with this well-observation lemma that the well-observation condition is weaker than the well-formedness condition. We have also completion lemma, which is useful if you want to work with this observable quantum Turing machine. Okay, so to conclude, I have introduced this observable quantum Turing machine, which is an extension of the quantum Turing machines which allows observations or measurements. This is more expressive, but not too powerful. It is not necessarily easy to find such a model, but it's enough expressive to represent any quantum Turing machine, any deterministic Turing machine. So it's a unifying model, if you like. And moreover, we have something which is more user-friendly for the halting of quantum Turing machines. And so one of the main applications is, in fact, the problem of the universal quantum Turing machine. Turns out that at the moment there is no universal quantum Turing machines, and in some very recent papers, two of them concluded with that in order to find a universal quantum Turing machine, we have to have a formalization of the classical control. Okay? It seems to be the main limitation to the existence of a universal quantum Turing machine. So here the idea is that with this observable quantum Turing machine, we have this representation of the classical control. So it's one of the main applications would be to try to find a universal quantum Turing machine in this class of Turing machines. Okay, thank you for your attention.
Okay. Before we turn to the questions, a quick question on my part. Is Leahy here?
Yep.
Okay. So I think we can safely take 5 minutes or so for questions. Go to it.
The restrictions you're putting in order to not be overpowerful, can't they just be motivated by the fact that you want the description of your machine to be finitary?
In fact, there are two descriptions. There is the description of the machine and the description of what the environment is doing.
Yes.
And it's, yeah, that's the point. In the previous cases, the description of the environment could be infinite. And in fact, we restrict the power of the environment until we have this finite description of the action of the environment. Yeah, this is exactly that.
You weren't saying anything about the frequency of the measurements, right? That if you measure too frequently, then by the zero effect, your machine won't evolve at all. And if you don't measure too frequently, then there's no difference with the...
No, the frequency of the measurements is fixed. It's we measure between every transitions, before and after every transition.
Okay. Sorry, I missed that. Yeah, just a second.
And what is it before and after? Why not just...
Okay, so the idea is between. Okay, what we want is between, but we want to measure before the first transition and after the last transition. So since and since when you apply two measurements, it's just equivalent to apply just one measurement.
Okay, I guess if there are no other questions, we, by my watch, have about a minute before the next talk.